Hello, everyone. Thank you for joining our webinar on data governance with a feature store. Today we have Jim and Alex who will be the presenters for our video today. And just a few comments before I pass it on to them. The presentation, the webinar is being recorded and you will receive by email after the webinar. And please send us questions using the Q&A chat button, so we can make sure that we get to answer your questions during the presentation. But don't feel shy, feel free to send us as many questions as you would like. We are here to answer. With that being said, I'll pass it on to Jim.
Hi, thanks Natalia. Welcome. This webinar is going to be about data governance and a feature store. And we're going to extend it a little bit to data governance in the entire AI data lifecycle. So I'm Jim Dowling, I'm CEO of Logical Cox. I'm joined by my colleague, Alexandra Ormenison, and Alex will do the demo, and I'm going to do a bit of talking at the beginning. So the demo will probably be 10 to 15 minutes towards the end of this presentation. But please ask questions. I'll stop. I'll try and answer them as I go. Okay, let's get cracking. So we're going to talk about feature stores in general, but we're going to talk specifically as well about our feature store, the Hopsworks feature store. And the Hopsworks feature store, it was the first feature store, first open source feature store to be released. It's now the only managed feature store available on AWS and Azure, and it's an enterprise feature store as well. So what you can do in it is you can create features, you can reuse them, share them, and you can see I've highlighted govern. We can talk about how we can govern features throughout the AI lifecycle. It's a little bit different to other feature stores out there. It's a very open platform. You can do feature engineering in any Python environment or any Spark environment, and it has tremendous scalability, latency, and security properties. But we won't go into too much detail on any of that today. We're going to stick primarily to the governance properties. So the platform is being used by a lot of customers around the world and a lot of leading companies. It's actually the leading feature store in the world by customers adoption. And what a feature store does is it really just helps you get your enterprise data. I'm going to draw a bit on the screen. I hope that's okay. It gets our enterprise data in our data stores here. And we then convert that data into what we call features. And I'm going to explain what that is in a little bit. And these are features get stored here in the feature store. And the conversion we call feature engineering, transformations of the raw data into these signals, compressed signals that we use to make predictions with. And to make the predictions, we need to train models. And when the models are running in production, so a model that's running 24/7, it needs to go back to the feature store and say, hey, I want to look up some information about this customer, maybe their purchase history, maybe their credit score, all that kind of information. It won't be in the app. It goes to the feature store to get that information. And then we can make our predictions when we retrieve those feature vectors. But we'll go into this in a little bit of detail. I'm actually going to talk about the feature store first, and then we'll go into AI governance in general after that. Now, I did mention that I will cover the whole AI data lifecycle, not just the use of features in the AI lifecycle, because you have to treat it as a whole. You can't govern part of the pipeline and then leave other parts ungoverned if you want to be compliant. So Hopsworks as a whole, it manages, in fact, the whole lifecycle. It's a very open platform. We have a lot of customers who use platforms for model serving, third-party platforms for model serving, or model training, or even feature engineering you can do in Databricks or SageMaker. But one of the challenges when you're a data architect and you're trying to ensure compliance throughout the entire AI lifecycle is, how do I deal with all the steps? The data will come in as raw data. We're going to engineer features. We're going to have them in our feature store. We're going to train models. So we're moving from left to right here, and then we're going to run those models in production, and they'll generate data that needs also to be monitored and potentially fed back into the system. So our platform actually provides functionality at all these steps. It's a complete end-to-end platform. So we're going to talk a little bit about what it means to have metadata about features and then going to training data sets and models and even model serving. So let's move on, and we'll get started with the very basics. what is a feature? I understand that many people here might have data backgrounds, and when you hear the term feature, you think functionality or capability of a system. Feature is just a piece of data. It's a piece of data with a signal, and it's not necessarily a copy of the data from your data warehouse. So what we're showing here on the left is raw data. Maybe in our data warehouse, we have the gender of a person, and we have only 2 genders here. You could have a third one potentially. And that is stored as maybe in a num or a string in our data warehouse. But typically when we want to feed it to a model, we're going to convert it into a number or a categorical variable is what we call it. So the categorical variable could be stored as a one-hot encoded vector ultimately when we feed it to the model. So it's not going to be in this stringified form later when we train the model. And the numbers that we have here, so we might have in a database, we might have a timestamp, and it might be a Unix timestamp. And we might convert that or squash it into a number within a range between 0 and 1, because those numbers between 0 and 1, they're normalized numerical features. They're easier to train models with. So we get our models can easily find minimas by basically working better with data in a very tight range than having this very wide range of values. So converting that raw data into the actual data, the features that we use to train the models is what we call transforming the data. And here you can see a lot of enterprise data is in tables, in data warehouses, in data lakes, in operational databases. And we write these featured transformation jobs or pipelines to take that data and turn it into features. So when you have features and you have many features, then you can have what we call a training data set. That's a set of features. And we have a label as well associated with the training data because we're assuming supervised machine learning here. So if we're trying to predict churn of a customer, we might have a number of features, 1 to n, and we might have an ID associated with this training data set for each row in the training data set. Might be the customer ID, for example. We're not going to try and train using the customer ID because there's no signal in it. But the features such as how long the customer has been a customer, how often they've bought the product, when they've interacted last with the company, these are the type of features we would use. And we put them together into a training data set, and we can use that to train models. So we call the set of features together groups of features in our platform, and then the individual rows we're going to call a feature vector. So each one of those rows can be used to make a prediction. So let's move on. That's the basics. Now, the data isn't always going to be from data warehouses or from operational databases, so OLTP databases. It can come from data lakes, and it can come from message buses, and it can come from potentially Excel spreadsheets. I mean, there's a variety of different sources that your data can come from. So we'll assume that part of the enterprise data ecosystem is governed by, there are many platforms and tools out there to handle that. And we're going to look at what happens when we take the data from these platforms and we want to train models. Now, if you don't have a feature store, and many people run machine learning in production without a feature store, typically for every model that you want to put in production, we have models on the right-hand side, such as a customer lifetime value model or a churn model. Well, what we do is we write the code to transform the raw data. This is called the feature pipeline. It'll transform the raw data into the features, and then we can train the model with those features. When we want to use the model in production, we can use it either as in what we call a batch application, where we take in a bunch of data. We might take in a bunch of data about customer behavior, and then we're going to try and use the churn model to predict if they are going to churn or not. And that might be a typical kind of batch application. You could even have a live model or an operational model that will basically, an example would be fraud, where we take in a user wants to make a payment or buy something. And then before the payment occurs, we try and use the model to predict if it's fraud or not, and then allow the transaction to proceed or not. So we will need these features both potentially for the batch applications and also for the live applications. And that complicates things somewhat. And the single feature engineering pipeline is one of the benefits of the feature store I'll get into in a minute. And let's see if we have something in the chat here. Yes, I think Alex is hitting the questions in the chat. So I'll let Alex answer them for the moment. Okay. So one point to note here is that when you do write a message in chat, make sure to write it to everybody not just to the panelists, so that everyone sees your question. Okay, so yeah, so if you're following this approach, every time you put a model in production, you write a feature engineering pipeline, and that could be a significant effort. You might have to have a separate pipeline for training and serving because you want to compute the features when you're training and when you're serving. And if those training and serving pipelines differ, you get skew, and that can cause very hard to find bugs and huge operational costs if you don't know where the bugs are and your models aren't performing as they should. So the idea behind the feature store is that we centralize these features. We're going to store them in this data warehouse, if we will, for machine learning features. And you write a pipeline, a feature engineering pipeline, once as far as possible. You take your customer data, your transactions, your financial transactions, your third-party data, and these feature engineering pipelines feed the feature store, and we're going to have our features in here. So we have F1, F2, F3, all our features here. In our platform, we actually, when we take in a group of features from a single source, maybe a data warehouse table or maybe from a data lake table, we typically ingest them as a data frame. So we'll ingest a lot of them at the same time. And that's a pretty common case. You might have customer profile data and you have 10 features associated. So we ingest those as what we call a feature group. But once the features are in the feature store, what we can do is we can basically reuse those features to train models. So adding a new model does not mean that we need to write a new feature pipeline. We can basically take the features, we can join them together, create training data, and then train the model. We don't need to perform feature engineering necessarily at this moment in time. We can just join features together, get our training data, and then when we have a model, an operational model running live, we can go back to the feature store and say, give me the feature vector, the row of features for this user, for example, and you get it back at low latency, and then you can send that to the model for predictions. The feature store has two kind of APIs. One is the low latency one when your model is running in production, the operational model. And then we have the batch API where we want to create training data by joining up the features together and saying, this is my training data set. Please give it to me in a file format for the machine learning framework I'm going to use. So I want CSV maybe for scikit-learn. I want TF-record for TensorFlow or NumPy for PyTorch. And give it to me in my object store in S3 or give it to me on my file system so that you can then train it from the environment you're going to train your models in. It could be SageMaker, Databricks, or even Hopsworks. I see Alex is answering questions furiously here, but I'll just have a look at one in the Q&A. Can we access the transform function at serving to transform input examples? Yes, so transform function serving, okay, without feature store in the pipeline, we'd embed transform function into the model to ensure that it's using the same transform function during training and serving. So there are different, you can classify features. I'll just make a comment on this for the moment. Some features can be pre-computed. Actually, you'll find, from our experience, most features can be pre-computed. Maybe you have activities on your website, users click, they get pushed to a topic in Kafka. And then you have a pipeline that basically computes how often the user has clicked on your website in the last 5 minutes or 10 minutes or hour, and it writes to the feature store. So it's kind of outside the application itself. And sometimes you do have applications will provide some pieces of information, maybe user types something into a form, and you need to then transform that string into a one-hot encoded vector, for example, categorical feature. So those transformation functions do need to be applied both in the serving infrastructure and in the training infrastructure. And there are different ways of doing it. We had a talk at the last Spark Summit about this. One way is that you can use frameworks like TensorFlow, where you can actually do some of the transformation in the model itself. So you can embed with these one-hot encoding or even normalizing numerical features. You can do that inside the model. You just pass in the string or you pass in the number, and then the transformation will happen inside the model. In other frameworks like scikit-learn, you do have scikit-learn pre-processing functions. And in our case, what we do is we load that scikit-learn pre-processing function into the serving infrastructure. For example, in KFServing or in Flask server, you can do it inside the predict function, or you can do it in KFServing in the stage before you call the model. called a transformer function. So you can do that code in serving and then also in training to keep it consistent. But I didn't want to get into too much details in this webinar. There's a lot of information out there already about this. Okay, I'm just going to click on that as being answered live. Okay, so no, I can't. Anyway, okay, great. So, so features are going to come into the feature store from many different sources. They can come in through your event buses, your operational data lakes, your databases, your data warehouses, and your data lakes. And they'll be updated at different frequencies, or what we call cadences. And you can have in our platform, we support any Python client or any Spark client, and we also support Spark streaming. So what we ingest are in fact data frames when we're copying the features into the feature store. So it's going to be a Pandas data frame if your feature engineering code is in Python, and it'll be a Spark data frame if your feature engineering code is in Spark or in PySpark. We also support external tables. So you might have a Snowflake database over here or a Delta Lake table, but we can actually also mount those as what we call external feature groups or on-demand feature groups. So you're in the feature store, we have these groups of features that we ingest together as data frames, and mostly they're cached or stored in the feature store. In the cloud, we actually store this on object storage. So this data in the offline feature store on object storage. There is also a low latency database called RonDB, which gives us the low latency access for online applications. So single millisecond latency to retrieve the features. So I'm just going to go through that. This is the basic way we get our data into the feature store, and the two main clients that we're interested in are the online applications that retrieve the features, and then we have the data scientists who want to create training data, and batch applications that are retrieving large volumes of feature data. So this is basically the very brief introduction to the feature store. There are way more capabilities than I have time to cover right now. But there are many more references as well you can look up. If you go to our website, logicalcosts.com, there's quite a lot of good information there. And featurestore.org is quite a good site as well to find out about many different feature stores out there. What I'm going to talk about now is AI data governance. And AI data governance is very similar to classical data governance. So classical data governance is the exercise of authority and control over the management of your data assets. So how you plan and monitor and enforce the use of data, you look at the data quality, policies for who can access the data, when and how, ensuring regulatory compliance in the use of your data, ensuring risk management if you do have some sort of breach, then you have measures in place to handle that those breaches, and then how you do business process management and business policies around data. And you can plug in just AI data for data and say, well, you know, I'm kind of done. I do this already for my data lake and my data warehouse. There's not really much new here. But in fact, the regulators are saying, yes, there is something new. AI data is different from classical data. And many of you will have heard about this, but there was a proposal last week that got aired, because probably it'll come into force at some stage in the near future, to regulate AI in the European Union. And we saw with GDPR what happened with data, that this has pretty much gone global with the Californian version of GDPR in the States. You know, being able to control and give people rights for how they can use your data, and giving the user, the owner of the data rights were new concepts at the time, but now they're pretty well established. So these are the main points that I distilled from those proposed regulations that got aired last week. It's called the Proposal for Regulation and the European Approach to AI. So the first point is that data sets, AI data sets that we use to train the models, but also for serving data, they should be relevant, representative, free of errors, and complete. It's, you know, very kind of ambiguous, but really what it's trying to say, representative is interesting. That means free of bias, is my interpretation of it. Relevant, meaning that we don't have obvious things left out. Maybe again, bias is one of the things that we're worried about here. And then deliberate errors, which again might cause problems, maybe cause your self-driving car to crash. And then they're complete. Again, that we're fair to all the people who are affected by these AI systems that make predictions. So we need to have extra support for managing our data sets in AI above and beyond what we typically have in data platforms. And Provenance is a new one, and we're going to actually do a demo on this because this is a very important and interesting part. And particularly if you're thinking of putting together many different parts of your AI platform, you're going to buy the best of breed model serving infrastructure, model training, experimentation, and feature store. You will have to manage provenance all the way through that. The traceability of decisions made by your models back to how they were trained, what programs were used to train them, what training data set was used to train those, what features went into that training data set, and where those features came from. So we'll do a demo on that in the Hopsworks platform. And also then to enable the user to understand and control the AI system. So how can a user know that the predictions that were made, this is explainability, it's a hot potato. I'm not going to go into too much details on it. Many of you know the problems with deep learning in terms of explainability of decisions made by deep learning systems. And obviously, classical AI approaches have solutions like Shapley and feature importance, but deep learning is still a hot potato there. Number 4, to establish and document a risk management system. That's pretty straightforward. Again, it's similar to what we have already for data systems. And then finally, to guarantee accuracy, robustness, security, and human oversight. And many of these are kind of common sense at some level, and they will be open to interpretation. I mean, I think an analogy I have used internally with colleagues is that in the gambling industry, there is a regulator who tries to make sure that any online gambling companies identify consumers who are at risk of becoming addicted. And it's very hard to draw a red line to say exactly when that happens. So there will be some level of, I guess, at this level, the human judgment will come into play as to when these properties are met or not met. Security obviously is a little bit more stringent. So you may ask yourself, well, can I use one of my existing metadata platforms or governance platforms to manage all of this AI? And there are lots out there already today. I just highlighted some of the better known platforms. In open source, you've got Atlas, Amundsen, and Marquez. These are primarily for data, and similarly, Calibre, Relation, Informatica, and Cloudera SDX are primarily focusing on data, and in the cloud, there isn't maybe as much right now. And they're really just metadata catalogs primarily, not doing governance so much. So I make the claim that most of this, what we need, is missing today. The kind of support that you need with a feature store is that some of the mechanisms that you'd like, I've highlighted here. So if we want to start with achieving compliance, we need to have mechanisms for achieving compliance. We need security, so we need to manage sensitive features. And we'll introduce a mechanism we have called schematized tags. So tagging, many people are familiar with. Schematized tags is where we have a schema for the tags. So they're types. It's an integer, it's a Boolean, it's a string. It could be a list. Sensitive features, role-based access control, so security, deciding who can access features. Audit trails to see who has done what to features, and then being able to certify assets. So for example, is this feature good enough to go into the production feature store? Or is this model good enough to be put into production? So who is going to certify that? Will there be human involved in the loop to make sure that somebody is ultimately responsible for that and accountable for that particular action? So governance, metadata stores and governance platforms also give you not just the ability to govern things, but to help you improve the productivity of the people using the platform. So if you have features and you're able to search for them, tag them, and you're able to query and preview the data, you're able to organize your features with a taxonomy, and you're able to collaborate between different users, then this can really help improve the ROI of your machine learning or AI system or platform. So I'm going to go through some of these capabilities in our platform in particular today. Now, what data is specific to AI? And this is an interesting question. We know that the data in the enterprise data, we have data warehouses, data lakes, events, buses, and so on. But if we start here and look at it, this basically captures all of the data, as far as I can tell, from when you get raw data coming in from the enterprise. We turn it into features. We have this transformation step, compute features from the raw data. And the features themselves, we join together to create training data. The training data we use to create models. And when we create models, we spit off a lot of training artifacts. There's experiments that can help us reproduce the models, because we can go back and say, this was the training data used, this was the program used to train it. We have the logs to see who trained this model and how it was trained and what were the hyperparameters and so on. And then the models themselves, typically we have a model registry where users can browse and see which models are available and deploy them into production. Deploying into production means either using it in a batch application or in an operational setting where the model will take requests over the network, and or it's embedded in an application. And that model then itself, when it's being used, will generate logs. So all the predictions made on it, all the statistics of its performance can be saved and they can be fed back in. So we get a virtuous cycle here, this flywheel for data. We can obviously monitor things like the KPIs of our models and have observability into their performance, but we can even generate new training data. So when users make predictions, and we can later find out the outcome of the predictions, we can actually feed that in as new training data to improve the quality of our models. So this is the data that we have. The only other one here is these feature vectors. So we saw earlier that the model serving infrastructure can use the feature store to retrieve the pre-engineered features. And that's that last part. So this is the data that we have. Where does this data get stored? Well, it depends on the systems that you're using, of course. I'll just name a couple of systems here. So we have the Hopsworks feature store over here, which is where you can store your feature data and training data as well. And it will be stored and can be stored as well on an object store. Many people use MLflow for managing experiments. So you could have a separate MLflow server to manage that, maybe using Databricks. And then you can have different model serving infrastructures. I'm going to mention Kube for model serving, which is probably the most popular open source one, but SageMaker is also widely used. So if your data is being spread around these systems, and then this one is really a question mark, I guess, at this point. There's not many mature solutions for managing the data that's generated by model serving infrastructures. So I'm going to just show you how we split up these data assets that are created, the AI data assets. I'm going to start on the left. So the feature data, which are the actual feature data, the features themselves, in our case, we store them in our file system. This artifact is our file system called Hopsfs. And this ultimately in the cloud, it will store the data in a bucket in S3 or in Azure Blob Storage container. But the larger volumes of data are stored in this artifact store. And the smaller volumes of data are stored in some kind of meta store. So metadata about features, about training data, schematized tags, provenance to find out, which training data set was used to train which model, the experiments that we run, the metadata for those, the model registry metadata, and then the metadata about models themselves that are running in production. Now, even when you perform experiments, when you train models, when you compute features, you generate a lot of logs, and these will get stored in a file system typically. And then the models themselves are typically files, so that's why we store them in the artifact store, which is, you can think of as being the file system. It might be an object store like S3 or Azure Blob Storage. In our case, our meta store is RonDB. It's a fork of MySQL cluster, and the inventor of it works for us. And our file system is called Hopsfs. It has the HDFS API, but the data is actually stored in the cloud in object store. So you don't pay extra. The data is separate from, we separate storage and compute when we run Hopsworks in the cloud. And that's the file system where the artifacts are stored. Now, if you have all this data that's being created, what mechanisms do we have available to govern these assets? So to ensure that we meet some of the new coming regulations in AI, I'm going to highlight three of them, three of the mechanisms that we support in our platform. And the first one is related to the feature store. So in the feature store, when we ingest data, features into the feature store, what we want to do is ensure that the data that comes in there is free from bias, that it's complete, as we saw earlier, and that it covers all of the expected uses of the data. Now, there are some different frameworks available, like Great Expectations is one for Python. There's another one called DQ for Spark. We build on DQ currently, and I'll just show you some of the syntax that we provide and the UI support we have for doing this. So when data is ingested into the feature store, you're able to encode rules that, or what we call constraints on the data to ensure that it meets the expectations that we have. And this helps us from one of the problems that you have when you have models running in production over here is that if somebody shouts bias and says, hey, this model that you're running in production is biased. And a good example was last year, Apple had an insurance product that they released, and females in the US noticed that they were biased again. So if they had higher income than their partner, who was male, then they could potentially not get the insurance product, but their partner got the insurance product. So what they found out was, after a lot of hard work, was that you have to go from the model back to look at how it was trained, the program that trained it, the training data, the features that were used to create that training data, and then you had the data imported from some other sources. What actually happened that time was they used data from the 1990s to train that model, and women's incomes at the time were substantially lower than they are today, and that's why the model had bias. So often people say that it's not the algorithms that are biased, it's the data. There is some truth in that, but you still have to check both. But the important point here is that if you validate the data for not having bias before you ingest it, to ensure that the feature data being ingested, for in this case the mean income of females of the data being ingested, is not significantly different from the data that's already there, the mean income already there for females, then if we have a rule like that, then we'll prevent us from ingesting that data in the first place. And that'll prevent you all the costs involved of going from this accusation of bias from your system in production, and we're getting at that particular problem at source. Another problem is even when you're using what you think is really good data and you've trained a model, you still will need to evaluate that model on many different slices of the data. So if it's using it against consumers, you might take different groups of consumers, and you might have slices based on gender or ethnic group or whatever you think might be a source of bias, and you evaluate your model against all those different slices. And only if that model passes all those tests should you move that model into a registry. And obviously you can automate much of this with CI/CD pipelines, and I'm not going to go through that, but these are important tests that you should do before you run your machine learning in production. And when you are running this model in production, you would like to evaluate that model and constantly evaluate that its performance is not degrading. So we look out for things like what we call drift in the models, so drift in the data that's coming in, or in what we call concept drift for models that's not predicting correctly because COVID happened and the data it's trained on is no longer valid. I'm going to examine how three mechanisms we have for supporting data validation, model analysis, and model evaluation in Hopsworks. So we start with data validation. So in version 2.2 of Hopsworks that we just released, we built in support for data validation rules. You can define, here we have a rule here, this is code, and saying that the rule has firstly it has a condition saying the minimum value should be 0. And if it's not, I'm going to emit a warning. We have another rule called the max value should be 1 million, and if it's not, that rule isn't true, I'll emit an error. So if we have, this rule is now called an expectation sales, and we can apply it to a feature group. I can say here's this feature group, I'm applying this expectation to it. So in this case, what will happen is that when the feature that we apply this expectation to, when we ingest the data into the feature group, this rule will get tested. And if the sales value or whatever the feature is that we're applying this expectation to, if it's less than 0 or greater than 1 million, less than 0 will get a warning, and if it's greater than 1 million, we'll get an error. So you don't, when you're writing your code, and this code down here is code to just ingest data into the feature store. We get a data frame, and then we call insert on the data frame into the feature store. These rules, the data validation rules that we defined and attached to this feature group will get executed, and then we get results. And we see in the UI here, we can see some of the visualization of the results. These are the actual results down here. And we can see that there was, 1 alert and 5 successes. And these are 2 of the expectations that we had that encapsulate the rules. The rules here are minimum and maximum, and the expectations are applied to the feature called year, or the feature is called salary and commission. I think Alex is, you're getting the, okay. There's questions there, but I think they're being handled. Okay, so that's data validation. Now, the second step was, I said, how do we evaluate our models against different slices on the data? Now, this is a pretty broad area. There are some commercial vendors who have tools in this space. There are open source platforms to support this. We support the What If tool. It's a plugin to Jupyter Notebook, and it's also available as a plugin to TensorBoard, which is also included in Hopsworks. So this is just a quick visualization to see how you can use the What If tool. So what you can do is you can use it interactively, as is happening here. We're visualizing a lot of data points that we can see here on the right-hand side, and you can see this is the census data, if you're familiar with the US Census data set, which is quite well known. And what you can do is you can basically visualize a relatively large number of data points. So I think it scales pretty well up to about a gigabyte of data, but beyond that, you'll have to subsample your data if you have more data than that. So you can visualize the data, you can click on individual data points and look for outliers, and then you can pretty quickly find out interactively what kind of problems you have, and then write tests against those problems. It's a pretty good tool. The third part, which is that when we have a model running in production, well, how do we monitor that model and ensure that we don't have drift or outliers, or whether it's behaving as expected? So what we do here is that we now in 2.2 version of Hopsworks is supporting Kubeflow model serving. So you connect your Hopsworks cluster to a Kubernetes cluster, and then we log all the prediction requests, or what we call inference requests, to Kafka in our platform. And then you can have a Spark or a Spark streaming job that will use the statistics from the feature store. So it will basically say, give me the descriptive statistics for these features, and I'll compare the same descriptive statistics I compute in the Spark streaming job against the training data statistics. And if they differ significantly, so if there's drift, then we can alert. And we can write results back to the Hopsworks platform. Some people are calling this an evaluation store. We think it's going to be part of the feature store as a component of it. Okay, so that's the basic governance covered. Now, I will briefly cover what security we have in the platform, and I'll go through it relatively quickly. There is a good blog link here if you want to read more details on it. And I go through authentication, authorization, accounting, and auditing in the platform. So when you run the platform in the cloud, in the managed version, Hopsworks.ai on either Azure or AWS, the cluster itself, it supports single sign-ons. We have single sign-on. Here we can integrate it with platforms like Azure ML, SageMaker, Databricks, Kubeflow, and the jobs. If you run jobs on our platform, they can use an IAM role or a profile to access native cloud services, either in Azure or on AWS. Internally, we have these things called projects, which are really sandboxes, security sandboxes that I'll describe in a second. So firstly, if you're going to connect Hopsworks to other platforms, typically virtual peering is what you would do. You would deploy your Hopsworks feature store to a VPC in AWS or into a resource group in Azure. And then you can use virtual peering so that it can connect to Databricks, and you can do your feature engineering on Databricks, or you can do your model training on Databricks, and then get your features from Hopsworks as needed. And the same for model serving, of course. And the same is true for SageMaker and other data science platforms. If you're using Hopsworks in the enterprise and you have Active Directory, or if you're using OAuth 2 for identity management, you can set up Hopsworks with single sign-on. Internally in the platform, we use certificates everywhere. So it's all X509 certificates to ensure that all data in motion and is encrypted over secure channels with certificates. And also user identity internally in the platform is using X509 certificates. So in fact, what we have in the platform is we have this notion of what we call projects. So when a user is a member of a project A here, and you're a user member of project B, we actually create internally a different user identity based on a certificate, an X509 certificate for each project. So when Alice is in project A, Alice really can only access the resources or assets in project A. If Alice wants to read from project B, it won't work. It's a different user, project B Alice user who's active in this project. So you can really have sensitive data in a shared cluster in our platform. Now, if you have different projects, you would also like to share data between them, you can do that explicitly. You can say this data set, such as this feature store, this production feature store, will share read-only with this development feature store project. And that way you can have users develop their features in the development feature store and then join them with features from the production feature store just to make sure everything works before you then decide to move your features into the production feature store. And we can share many different assets like data sets in HopsFS, even Elasticsearch indexes, feature stores, and Hive databases, and Kafka topics can be shared between projects. Hopsworks integrates with Kubernetes because we use certificates internally. This works quite seamlessly. Projects in Hopsworks get a namespace in Kubernetes, so you can create a namespace associated with it. You can do it explicitly yourself, or we can create it if we have access to Kubernetes permissions to do so. And when you run pods in Kubernetes, so we support things like running notebook servers in Kubernetes, Python jobs in Kubernetes, or KFServing, Kubeflow model serving in Kubernetes. So we launch a pod, and the pod will have an X509 certificate and a JWT token to access the REST API to Hopsworks, and that way it can actually use the services in Hopsworks from within the pods running in Kubernetes. So moving on, so if we look at audit logs and how we do auditing in our platform, and that's obviously crucially important for governance. In the feature store, explicitly for these groups of features, when we ingest data, we're using a framework called Apache Hudi to store the offline feature data, and we store an audit log of that. So every time we do an ingestion, we'll get an event with how many new rows were updated, added, or deleted, and you're able to track this now in the new UI to the platform. There is also an audit log for all REST commands that you make directly on the platform that we store in our file system and can be accessed later. So that's the brief overview of the slides, and Alex is going to go through a demo now, and the demo is based on provenance. We're going to go look through this problem of, I have raw data here, I compute features, we have features computed from that data, and the feature engineering pipeline is used to compute these features, and the features we join together to create training data sets. There's a one-to-one mapping between each training data set and the model can be served. So one of the questions you have here in terms of the new AI regulations being proposed is, well, I should get my bias problem here. How am I going to go from bias here all the way back? Alex will look at the issue of personally identifiable information. How do and we have one of our customers is actually doing this, where they are able to track using tags, features that are tagged as PII. They can go through this provenance graph to find out, okay, what training data sets use these PII features, who was the user who did this, what models were using it, and it enables you to give you full visibility of what's happening in the pipeline. There is some really great tech behind this. If you're curious, Alex had a paper at the leading Usenix machine learning systems conference called Usenix OpML last year about this. I'm going to hand over to Alex. If I stop sharing, are you sharing now, Alex? Or? Okay, I'm not sharing right. Stop share, yes, there we go. So Alex can take the screen.
And I'm unmuted. Okay, so can you see my screen? Yes, okay. So I will go through what Jim said. I will go a bit through the provenance mechanisms, through the search mechanism, and how you can also use tags to amplify this and augment your data governance mechanisms. So first off, since there might be new people here, I will go through a small introduction on the feature groups, how they look in our platform. So this is the feature groups. You can see a list of feature groups here. You can go inside them. You can see the statistics that were computed. You can see provenance. You can preview data. You can just a second. Prefetches some data. You can see the jobs. Let's see. Click on one and see the job that was used to generate it. This one has the games features. This one would have a yes. So you can see the feature, the job that generated this one. Again, you can then see the training data sets that were generated with the same statistics and provenance and more information. You can attach text to them. And for our newer version, in version 2.2, we also have a different UI, and you can attach the validation rules and the expectations that Jim presented. And I will jump now just shortly to the new UI to show you how to do that. So in the new UI, again, this would be the project. We go in the project, we look at the feature groups. This feature group, I know I computed before, has some expectations. And this is similar to the ones that Jim had in the presentation in the print screen. So in here, you can look at the expectation. You can see there's a minimum of 0, as he said, a maximum. You can see an activity list when they were run. These were run from the same notebooks. So they have the same timestamp on them. And you can add more, and you can. Okay, yeah, you can look at the activity as well. I mean, you can look at the whole activity in here and check when and what happened. So you can track the whole activity list to see what happened to your data in there. If I go back to the old UI, again, you can create feature groups easily from the UI. You can create them from notebooks, as I will show later if time allows. You can create training data sets in the same way from the UI or from the notebooks programmatically. And we can search for things. So for example, I can see here that I have games. I can go to my top level view. I can search for games, and it will highlight exactly what's matched in here. So it matched the title, the description. I know that I have a tag called location, so it will find something else that I attached to, and it will highlight that. And this is the search part in the platform. Now you can do everything that I will show you here in the notebook. So the last thing that I show in the front end is the tag mechanism, a very simple way to attach tags. We have some feature groups here that I generated before, and for tags, you have to define them beforehand, and you can attach values to them. Now the tags, I will jump a bit to the examples here, so you can follow the examples on examples.hopsworks.ai for tags. We allow for fairly complex tags that you can attach. So we follow, let me go to the top. We follow this JSON schema. This is the reference that we follow. We didn't invent it, someone else did. You define the structure of your schema using a JSON itself, and you use that as a, let's say, type for your tags. And then these tags can be from a string. So this would be the schema that determines that a tag has to be a string. And this can be a more complex one with a first name, a last name, some age, a hobbies, which is an array of things. So you can go fairly deep. You can also say which fields are actually required in the tag, which ones, if these fields are the only one required. And you can set even rules on these tags as to min and max, similar to the validation, but a bit weaker. So the validation rules on the tags are a subset of what Jim showed, for example, for the features. Now, how do you do these in the notebook? Well, in the notebook, let's say that. Okay, Jim was telling me that I should jump to the provenance first in the UI. I forgot. Yeah. So in the views that I showed you before, I showed you that you have a list of feature groups, for example. Then you have a list of training data sets. You have a list of experiments in our case. You have a list of models that were generated. And if in the models you have different versions. So, okay, you can view them easily, but is it easy to explore them and to go from one to the other? Because this is just a list. So I can go from the feature groups, and with provenance information that I tracked when I generated them, we can see here that it tells me which training data set was created from this feature group. So I can just click on this one. It jumps me to the view of the training data set, and it emphasizes, it shows this training data set. And then I can continue again with the provenance, and I can see that now for training data set, I have multiple choices. I can go back to the feature group that was generated, so to my source data. I can go forward now to the models that were generated using this training data set. So now I have two of these, and to the experiments and their artifacts that practically generated these models. So again, I can just click on the model, it jumps me to the model. On the model, again, I can jump to the experiment that that created this model. And from there, I can go back to training data set. So this is like a whole graph that I can go, and I can go back and forth if I want from models back to the features that were used to generate it, or if I want, I can go upwards and see what was like, what artifacts used my feature groups, training data sets, and models, and so on. So how does this one look in code? So for the provenance part, let's say, the provenance API is included in our HSFS library. And this project is called Webinar. We just get a feature store connector. And as you saw in the list, we had a webinar feature group, and we can get the feature group. Okay, it awares me that I didn't provide a version. So let's say version equals 1. And since this one is the first feature in the pipeline, it doesn't have any sources, but if I regenerate this, it shows me that the training data set was created from this feature group, and this is the webinar training data set. I see the version of the training data set that was used, that was created. I see the project itself, and I can also see the application. So this can also help me to see exactly which application, who ran this application, and find out more about this. And then we can continue in our provenance exploration in the notebook by looking at the training data set. And again, I'm getting the version 1, and we go further, or we go again back and see what was the source. Okay, we already know it was the webinar feature group. And what were the models? We have these two models. So exactly like in the UI, we give you the power to also access this information in like programmatically in your notebooks. These can be run in as jobs in the applications. And you can do this some things automatically, which I will show maybe such a use case in the step 6. And also you can retrieve the experiments that were used, like I said, to generate the models from the training data set. Again, another mechanism that you can use is the search mechanism. And we saw it in the front end, how to do it, but it's also available in the notebook. In this case, again, we get a connector to our feature store, and we start by searching for a feature. You can search by name, for example, in this case. You say webinar, we get both of the features. We change it to webinar feature group, we get just one. So it's full text search in here. It's backed by Elasticsearch. And you can search on multiple things, not just name. We can search, for example, on the tags that are attached. So the webinar feature group had 2 tags attached, location and PII. And since that one had both of them, if we use Boolean logic, so this is the query string from Elasticsearch. This is pure Elasticsearch. You can write arbitrarily deep Boolean logic in here. If we search for a feature group that, or for all the feature groups that have both of these tags attached, we will only get feature group like webinar feature group. But if it's enough for us to look for the location, the feature groups that have location attached, then we of course get both of them. And all of the operations that we can do, like all the search operations on name, description, tags, and other metadata that you can do on feature groups, you can also do on training data sets, and it will also soon be extended to models and experiments as well. Now, how does this help you in a practical case, let's say, again, in a notebook? So we saw that let's view it again. I attached to the feature groups here a PII, so it's a personal information. What does that personal information contain, or what does it tell me? So let me generate my connector again. So as we see here, the PII information, let's say, contains the fields that are personal in your feature group. Maybe you have personnummer, so a social security number and salary, and these fields are considered personal. However, you detected this, or someone decided to look at this and say they are private, maybe after the fact, after you've generated some training data sets, after you generated some models, and all of a sudden now someone tagged this with personal, and you want to explore and see what are your artifacts that are in trouble, let's say, and how do you find them? So these steps we did before. At some point, one of your colleagues attached this tag to a feature group and said, be careful, this contains private information. Then you can create a job, or even do it, explore it in a notebook. And we search in the feature store for feature groups that have this PII attached, as I showed in the search notebook. We get the project where this feature is, the feature store ID, the name of the feature, and the version. So with these informations, with the name and the version, we can of course get the feature group, and we can continue the chain as I showed you in the UI. So we have the feature group. Now we look for what training data sets were generated from this feature group. And now we use the provenance tab to step into towards the training data set. We get our webinar training data set. This is the metadata for it. Now we get the training data set itself. And okay, we know the training data set that was, let's say, corrupted, or it's maybe you want to redo it. And you go further to models. You get the two models that were generated from this training data set, and you also can see the experiments and, I don't know, check the notebook that was used to generate it, check the libraries that were used to generate it, and so forth, to modify it so that you maybe don't use these columns later on. So this would be like a use case for combining provenance, tags, search, to provide you with a more complex governance mechanism that can allow you to, let's say, fix your pipelines. Okay, thank you. I'll mute myself now.
Great, thanks, Alex. That was really great. So we're kind of, that's the end of the webinar at some stage. I think we have one slide. Maybe you can stop sharing, Alex, and then I can just share the last slide. So you can try Hopsworks out on Hopsworks.ai if you're interested in getting started. I had one slide left, I think. It's available as a managed platform on Hopsworks.ai. It's also available as an enterprise self-managed version you can install anywhere. And everything we showed today is available in community Hopsworks, the open source version that you can install anywhere. So it's also, you can find us on Twitter. You can find us also on GitHub. You can give us a star there. We're almost out of time, but there is one question that we'll try and get from the anonymous attendee. Two questions. You showed during the demo that you can explore and detect particular usages of your artifacts. Are there any other use cases that you're looking at? And then the second question is, how do you keep your provenance metadata in sync with your data? I'll answer question two, because that was in the paper, it's in Alex's paper. I was a co-author of it, so I won't claim to have done as much work as he did. But what we're doing is we store all the metadata in RonDB, the source of truth, and then Alex, in the paper, he showed how you can efficiently filter that and eventually replicate it with eventual consistency semantics to Elasticsearch where we're searching. In practice, the lag between the replication is on the order of 10 to 50 milliseconds or 100 milliseconds at most. The first point was, are there any other use cases that you're looking at? I'd love you to find some. You know, this is an incredible mechanism that we're providing. I think we're the first people out there. And, you know, just being able to traverse this pipeline graph, this provenance graph, and attach any arbitrary metadata to it and discover things. So, you know, being able to say who in your organization is using PII data and then send an email to them to automate that is really powerful. So I think that's it for the questions, and we're out of time. I don't like to go over, I know everyone's busy. So I don't know, that's it. Thank you very much for attending. Natalia, any closing words?
Yes, thank you, Alex. Thank you, Jim. That was a very interesting presentation. Just a reminder that everyone will receive the video recording because some people who join a bit late and ask for the video. So everyone will receive the video recording after the webinar. Thank you for joining us and have a great night or great evening, depending where you are.
Or morning. Thanks very much. Bye-bye.
Bye-bye.